So let's get started. Okay. So let's very briefly review what we have learned, because I think over the weekend and then it's not easy to recall every single concept. So real quickly, we start from the continuous random variable. So we will be finishing this set of slides. So we'll be having a quiz on Thursday. Okay. So after we should be able to finish this today. So a quiz on Thursday. So make sure that you notice we have quiz. Okay. So it's continuous random variable. So this is different from the discrete version. Okay. The discrete version, you can remember the discrete random variable. Discrete means you can list them out, right? So which means that you can list every possible value and assign probability to it, right? But the fact that now it's a continuous, you're unable to assign every single element, right? That is mean by continuous, right? Because it's a countable infinite, right? You cannot easily have that. You cannot count it. So that's why instead of giving every single element, you have to give a bunch of elements at the same time, right? So the most natural one is the cumulative one, right? Just asking what is less than or equal to a certain value, okay? This we call the cumulative probability function, okay? And it's integration, right? But this in general actually means such as sum of x, right? For x less than x, right? So that is the same thing. And sometimes this is called probability density function, which is the differentiation of the f, right? And you know the differential integration are the reversed by the 9-ips, so by the fundamental theorem of calculus, okay? But this density function, and the thing for you to remember is the for density function, okay? The area under this f curve, A and B, this area will be the probability x between A and B, okay? So that's the only thing we can remember. Okay. By the way, can you see the slides in case I haven't asked now? Okay. So the let me go to the next slide. So we just will quickly review a little bit. So the expectation is same idea. Okay. Integration, right? If you replace, you just remember the discrete case. You just expected x times px, right? Is the weighted average, and the weights are the probability. The same idea here, okay? Is weighted by the density, okay? If you learn physics, that is some or engineering, then you will figure out this is very natural thing to have, okay? And the variance, again, is same as the discrete version, okay? Squared deviation of the mean, the weighted by its probability. So this is this guy, right? And this probability, and this is the height, okay? The same concept, okay? I hope that's all right. Since we covered, but just a some reminder for those, okay? And recover uniform, exponential, we touch a little bit normal, and the key of the today is covering the normal, okay? And this chi-square, student T and F will be the period of things we do in the future chapter, okay? So that means that this will not be included in the quiz, okay? So the quiz will be focused on the first three, okay? Uniform, exponential, and normal, okay? There will be quiz on Thursday, okay? So let's go to the uniform and exponential again to a very quick review, okay? And uniform is equally likely within the relevant range, okay? the value is V equal likely between A and B, right? Just to remind you what the uniform means is, if A and B is here, it means that I pick up any distance, okay? Say unit distance, 1 unit, and I consider any unit, whether they overlap or not overlap, okay? As long as they have a unit distance 1, okay? The probability that the random variable equal to that number will be the same, okay? A number from here, same as number from here, and a number from here. They're the same probability, okay? And the density function, okay, is basically a bar, right? Just like this. Okay. The height is 1 over B minus A, okay? And the distribution function, okay, integration of density will be x minus A over B minus A, okay? So this are the things to remember, or you should pay attention to. And the mean and the variance, you should pay attention to this formula. But as we said, these two are just, we try to derive them, but we don't have, we need some integration technique. So that's why you just need to remember it for our purpose, okay? But you should able to see there's a logic behind how they come about, right? Although it's not within our scope of examinable material, but you should know how they arrive, right? I mean, at least in principle, how they arrive. But any question on this part? Oh, some question, yes. Yes. So someone asked me, Peter, I hope that's okay. I copied this question to the class. I think this is a very interesting question and also important question. So asking, at a particular point X, the population will be 0. The answer is yes. And for the distribution that's a truly continuous, okay, truly continuous, which is most of our case, and then the value of the random variable equal to a particular number is always 0. The reason why is because it must be 0 because add them all, everything up must be 1, right? So if it's not 0, you're adding many of them, okay? You will more than 1, okay? So that's why it must be 0 for a particular number, okay? You can imagine that that is also easy to understand. You have a particular object, you want to put, say, height or weight, okay? And say for pen, the length of the pen, okay? Or the weight of the pen. A pen may be weight like 10 grams, right? Usually we say, but exactly it's not 10, right? It will be 10 point something, okay? And equal to a particular value 10 will be very rare, okay? Or temperature of today or wind speed of today, usually you may not have exactly the number you have. So it's usually particular value will be 0. It's a very good question. I hope I answered the question, but usually it's not, usually it's always 0. Of course, there are cases that we call the mixed random variable, then you will have some probability mass at a certain point, okay? And the example like this, okay? Suppose you ask go to the survey, ask number of people who stay in hospital, okay? In that case, there are many people different days, right? Maybe even to hour, the minute, right? It's a continuous distribution, right? Now the time you spend in the hospital in a year, okay? And then in that case, you up to the second of the minute, right? Then the continuous distribution, right? But the thing that is a lot of people are not sick, not stay in hospital. A lot of them are 0, okay? In that case, 0 will be a mass, okay? But you will take away those people who are not staying in hospital, then you will be a nicely truly continuous. Peter, did I answer your question? Do you see this? So that's a little bit complicated when the real world data, but if you take away those kind of consideration, most of them continue to be fine. Okay, but there's in the real world it's much more complicated. But for our purpose, usually it is not the case. When we say continuous, is particular value will be 0. And I hope that helped you answer the question. But in the real world measurement, we must be stopping somewhere. So, and in some sense, in the real world, what we observe, right? Right? If you learn physics, you know that some way you cannot have perfectly accurate measurement, right? So that's why it is always, you cannot there's up to certain digit you have to stop. So in some sense, in the real world, it's always discrete, what we can see, what we can observe. But for all practical purpose, it's okay to assume these things are continuous. I hope it's more philosophical question, but for business application purpose, it's okay to assume certain things continuous, although in the world observe the discrete, right? Just you can ask, what is the time we have typhoon, right? And it's a follow exponential, suppose, right? But what we measure in the real world data is always discrete, but you can consider continuous. There's no harm to do it. Okay. Any further question? Okay. If no, then go to the next slide. Okay. Exponential. Just to recall, the binomial. Okay. Binomial trial. You have, suppose you have n trial. Okay. Each trial has probability P of success. One must be P fail, right? And when n go to infinity, P go to 0, and NP still positive, right? That will Poisson. Okay, we repeat a lot of time, and probability success is very small. Actually, it's a Poisson, right? And Poisson is asking how many times things happen in this period of time, right? And we learned last class that what's the time before and tick happen, right? If it close and there's no event, and what's the time until it happened? Time. Okay. It will be equal to exponential. Okay. And that's why you can see this is somewhat related to exponential. And why this is related to exponential is out of the scope of our class. We don't explain it, but just if you go further, study advanced probability class, they might explain why this is related to exponential, why this is time. But for purpose, this is the exponential is related to Poisson. And you just need to know this formula, and this formula is also needed. Okay. And of course, usually just need this formula, right? This is usually is not really needed because for probability, it's always this one is as far as this concerned, right? And the mean is lambda -1, and variance is lambda 1 over lambda square. Remember, there's no 2, there's typo. The version upload, so make sure that you take it away from your version. Okay. Any question? Is that okay? Just make sure you remember the things with blue. If it's something that you will be asked in the quiz, likely in the exam too. And that, okay. Any further question? If no, then we're going to talk about normal, which we briefly touched last time. So normal, as probably you know, we mentioned last time, it's also called, oh, there's some question. Okay, sorry, I just go back a little bit because someone asked me a question of, I think they asked me what's meaning of lambda? Is it the question? Oh, what is x? Oh, someone asked me what is the meaning of this. Okay, this means that this vertical bar is called given. Given the value of lambda, so we know the value of lambda. So lambda is not a random variable. Usually when you write probability, this is lambda is say number 3, lambda equal to 3, lambda equal to 4, equal to some number. So usually because we write x and y, sometimes there's 2 variables, but when we write this is a value we know. It's a constant. It's not exogenous, you can say. Somewhat given. It's called parameter. If you want, sometimes refer to parameter where we have this given. Same as what we learned, the probability x given y, the conditional probability. Okay, but anyway, go back to this normal distribution, right? And for normal, okay, is invented by Gauss mathematician. So that's why it is also called Gaussian distribution in the old days. And this this normal distribution actually is very versatile. Turn out to be IQ in the population, weight, height. All these things are actually related to normal, and that's what the bell curve. Okay, it's called bell curve. Okay, the bell. And you notice that the probability density function and the distribution function are all very complicated. Okay, it's something that you shouldn't supposed to remember. Okay, to remember. And to be honest, if not teaching, I would not remember this, right? Because it's our memory slot is very limited, right? You don't need to remember something that is not need to remember, but they are there because they are so important. I cannot just skip it from my slide, but just know there's something. But the key here you need to see is this function has 2 parameters, mu and sigma square. Okay. Sometimes people just write sigma, but the same thing, sigma square. But the key here is turn out to be these 2 parameters, okay, given this parameter, right, is the mean and sigma to the variance, okay? And that means that actually we talked about last time, this is the location, right? And this is the spread, okay? Okay. And you will notice that from the first set of the slides, we still have 2 things, right? The shape. We have skewness and we have kurtosis, right? Those of you who have done assignment, you will notice this the thing that I sometimes want to report in your assignment. You may or may not report, depends on situation, right? But skewness means how symmetric they are, right? And the bell, the skewness is 0, okay? And the kurtosis for the normal is very fun because regardless of what is the mu, what is the sigma, okay? Kurtosis is always 3, okay? So that's why we always said, whether we have excess kurtosis is -3, right? If the kurtosis is bigger than 3, right, we will say it's fatter than normal or thinner than normal. And remember, the kurtosis is talking about the tail behavior, okay? And if you do finance or accounting, deal with the risk scenario, okay? And usually people would put variance the risk, and this kurtosis is called the tail risk, or the catastrophic risk, or risk of extreme events, okay? Or risk of rare event, because looking at the tail, right, is the very rare event. Is that okay? Any question so far? If okay, can I have you say okay? Just to see how many people are around. Yeah, good. So very nice. Even though it's typo number 8, okay, you still have some reply. Okay. Okay. So now let's see what we have said in the graph, right? The green one is mean 0. The blue one is mean -4. So it's move location to the left. And the green one is the sigma is 1. The red one is sigma 4. So when you increase your sigma, then you become flatter because more spread out, right? Because remember, the area under the curve is always 1. So it must be, if you want the both more spread out, then the top should be down. And it's symmetric, you can see, okay? And turn out interesting thing is, even though it's spread out, the kurtosis is always 3, okay? So that is something very interesting thing to note. Okay, now we talk about very important concept we call transformation, and particular we focus on particular transformation we call standardization. Okay, and this related to what we call something we didn't cover, but you can check the textbook chapter 3. We call standard score. Okay, well, standard score is for any variable. Okay, we just subtract its mean over its standard deviation. We call it standard score. Okay, and this standard score, you may not understand why this is the case. Okay, but there, I think you also, the book would tell you, okay, in most of the real world problem, if you convert any data to standardized score, it is always, the standardized score is almost always between +4 and -4, okay? Or in general, most of the cases always between -3 and +3, okay? This is what we call the Chebyshev inequality, but we're not going to cover it, okay? But what it means is, if you convert it to standardized score, it's always between this number. And why you would want to do the standard score is because you want to compare ranking easily, right? Of course, you can do percentile, right? You can always change what's the value X to a percentile, right? You can change the percentile. Okay, but in the old days, percentile is not easy to see, to calculate, right? And that's why the standardized score is helpful way to do instead of percentile, right? And suppose, right, in your primary school, right, you got 90 points, right, for the math class exam, then probably it's okay, it's not very great, right? Because usually people expect you for the exam for the primary school math, you expect 95 or more, right? If you get 80, then probably your parents would be asked to go to the school, right, to explain why you didn't score high, right? But when you go to secondary school, right, and or in a college, right, if you get 80, then usually maybe you got an A already, right? So why is so different, right? all from 0 to 100, right? Because of the mean are different, right? And also the variance matter, because primary school, right, the variance is very small, right? Because look at the marks, right? It almost concentrated on say 95, right? So, and the variance is also usually maybe 1 or 2, right? Subdivision 1 or 2, right? So if you are 80, then it's very far away from the mean, right? But if you are in the college, right, and the distribution is always something like usually 70 something, right? And the variance is also like 5 or 4, right? And 80 is already is very high score, okay? So that's why we look at this, okay? So what's key here is if X has a normal distribution with mean mu, variance sigma square, standardize it, which means minus mean over its standard deviation is normal with mean mu, variance 1, okay? And the reason why this is good is because, as we said in the last previous slide, we do not have formula for this, okay? This is the cumulative function, right? We don't have this formula, different from the exponential and normal. We need to use calculator or look at the table to calculate. In the textbook in old day, we use C table, but now is 21st century, right? We will use Excel or other software to calculate, okay? If you look at textbook, to save space, they will only give you the positive number. The reason why is because it's symmetric about 0, okay? So to find textbook negative, right, we'll be using the 1 minus, okay? The reason why is the following. Hopefully you can see it. The 0, okay? If you want to find this area, negative z, the red area, okay? What you're going to do is look at the symmetric case z, the blue area, okay? The red and the blue are the same, okay? But how to find the blue area? The blue area can be found using the method you learned in the primary school, okay? Because the whole area is 1, you know the green area. The green area is from the table, okay? The green area of the table. 1 minus the green area is the blue area. And the blue area is the red area. Is that okay? So in case you use the textbook, but you don't need this trick, now you have a computer. But just now you know, if you look at the book, this is how you look at it. Is that okay? Any question? No? Okay. We're surprising. You're very good. So let me give an example. You will see. Okay. So now we have a standard normal distribution, okay, which is N01 using a C table, which we will not use it. We use Excel. We're using the Excel function called norm standard dist. Okay. For those of you who know Excel, doesn't really matter. Google Sheet will also have the same function. Okay, but we'll just illustrate through Excel. Okay. So we will calculate x less than 1.4. Okay, is this number. X less than 1.6 is this number. Okay, and in between this number. Okay, we will illustrate in Excel. Okay. Let me show you the Excel. Okay. Can you see my Excel? Can you see my Excel? Yes. So if you use Google Sheet, you got the same thing. So let me pick a question I'm going to ask. So the question is x less than, sorry, z less than 1.4 and z less than negative 1.6 and 1.4 z 1.6. Okay. So test. So hopefully you can see it clearly. Okay. So these are the question. Okay. So what we are doing, you're using what we call the norm standard this, okay? And then we'll put 1.4, okay? And then we will say true. True is the thing we need for our purpose. True is give you the cumulative function. If false will give you density. So for most, I think, for the purpose of a class is always true, okay? So it might be. Is that okay? Good. So this one, if you use the C table, you have to look at, do the subtraction. But for the purpose of Excel, you don't need to worry about that part. So normal standard distribution, you put negative 1.6, you put true again, as we said, always true for our purpose. We give you answer what we want just now, okay? And this one, okay, will be the difference between 1.6 and 1.4. Oh, sorry, I think I make a typo here. Okay, so that will be norm standard this 1.4 true minus norm this negative 1.6 true. Okay, so this is the answer that you can see from the example. Is that clear? Let me know if you have any question related to the Excel for this part. Is that okay? If that's okay, then I go back to the slide, okay? And show you this one, okay? So now it's no longer normal 0, 1, it's not standardized, okay? It's general, okay? With mean 20 and sigma is, the variance is 16. So easy, you can see sigma is 4, okay? Another question is asking you two things. First part, x greater than 0 and x is between 16 or 24, okay? And the good thing is x bigger than 24, we can replace it to z, okay? Through standardization, okay? Standardize it means you subtract the mean over its standard deviation, okay? So that's why both sides subtract 20, okay? And divided by 4, okay? And this guy is called standardized normal, okay? And this is 1. And the z is, we can look at the Excel, right? Excel can tell you z less than 1, okay? Using what we have discovered, right? And then you want subtract from it is the answer, okay? let me show you the Excel. Okay, so here is we have mu is 20 and then sigma is 4. Okay, and what we want is x more than 24. Okay, and in that case we also know z is bigger than 1. Okay, so let's do the z thing first. Z bigger than 1. Can you see my slides? Just make sure. So can you see my Excel spreadsheet? Okay, so z is bigger than 1. Okay, will be 1 minus z less than 1, right? Which is norm standard this 1 and then true. Okay, so let me copy. Is there any question? The reason why we 1 minus because this is asking more than, but the Excel will give you less than because this is the cumulative one. Is that okay for this one? Okay. No question. Now the other way around is to directly in Excel you can do 1 minus. Instead of giving standardized, you can give directly. They call normal this. There's no S the standard there. Again, you put 24. Okay, but you have to put the mean, which is 20. You put the standard deviation, which is 4. True. Okay. So give the same answer. Okay. And what the program do is exactly they convert the 24, you subtract the 20 and over 4, and you do the same thing here. So basically, the Excel would save you the time by minus the mean and over the sigma. So that is what it actually is doing. So which one to use, up to you. It depends on what you like and depends on where you get this mu and sigma. Okay. Is it okay for this one? Any question? If no, probably I go over one more slide. Sorry, I still have this one. Okay, x is between 16 and 27. Sorry, 16 and 24. Okay, so that is how you do in the Excel. Okay, 16 and 24. Okay, and you'll be norm this. Okay, 24, 24, true. Okay, minus norm this 16, 24, true. Okay. Make it smaller. Oh, this is visible now. So I guess this is that. So maybe let's have a break of 15 minutes. I'll answer any question you might have. Break. 2. So feel free to ask any question you may want to. Which one? Kid horn, I'm not. Okay. Okay. Kid horn with the summer. You calculate smaller. No. Kid horn. When you smaller because yes, because the thing smaller, the cumulative is smaller, so we don't need to one subtract. When it more, then you subtract. Just reverse. Larger than, you take 1 minus. Smaller than, yes, as it is. So in case ketone, you can see less than, then I just put the number. More than, I have 1 minus. But anyway, in case you see a question, please feel free to ask. So, because the mean is 1 over lambda. Oh, sorry, I replied wrongly. Just wait a second. And ask me true and false. And so in Excel function, when you have Excel, when you have true, is here. When you have false, you have here. There's only difference for the true false. Check why. But for the purpose of our class, we never use this one directly. So that's why always true for our purpose. So that's why when you see the Google Sheet, the formula only, they don't have even true. You don't have the option. You just put one number there. Excel still have it because same as the discrete version. There's some historical reason. So let me add some water right back. before we end the break, I want to ask you to do the pooling, because it's given by the asked by the faculty, ask everyone to every class to submit this. So let me know if you just I just submit that to the faculty. So it's not my survey, it's from the school. So just fill in what you like. I just submit the number at the end, so don't worry about that. It's anonymous. You just fill in what you like. So the two questions, but this first question I will just give you 3 or 4 minutes to do it. You also fill it for other classes, I think. Every classes will fill in, and then the faculty will decide what to do based on the preference. So at the end of the day, just how this class be conducted, the rest of this class will be based on decision of the faculty. So I mean, of course, upon your submission of your preference, but they will say whatever. Um, this just as your preference. Nothing but preference only. As I said, I mean, how the class will be conducted will depends on later announcement, and also depends on how the pandemic goes. So just this is a survey to be done, asked by the faculty. Okay, any more votes? If no, we end for this one. There's another question related to this one. I need to report this to the faculty. Any more? Okay. Okay, then just end this one. Probably you see the result. I don't know whether you see, but most of you prefer the online one for the rest of the class. So there's a other question. So we fill in, then we resume the class. So again, I'm not teaching the semester 2, so it's nothing conflict of interest of me. So just you decide what to fill in. Just to name it, this is only faculty purpose, not for the school. So the faculty reference. So give 2 more minutes, then we will end this pool. Any more one to fill in? Otherwise, let me just end this one. Otherwise, it's just too time consuming to work on this one. Okay. 10 more seconds. Okay, we just end this one. So I think different from the previous section, most of this, I think I should. Oh, yeah, I should share the result. Most of you actually prefer to under the vaccine is available. Okay, but I don't know when the vaccine is available. But anyway, for those of you actually not in Hong Kong, don't worry about for this class. The thing is that to make sure for this semester will be if we ever resume the face-to-face, we still have the Zoom option. I think at least for those who have legitimate reason. I'm not sure if you are in Hong Kong and you don't have excuse to can exam, but at least if you have good reason that you would still be able to exam yourself from attending the physical lesson. The Zoom will always be there, so don't worry whether you want it or not. But anyway, I think the school will announce sometime soon once this exercise has once they decide what to go with that. Okay. Any question? I hope that's okay before the everything. Okay. If there's no further question, I will just briefly go over some of the proof. I just highlight as same as before. I just highlight the key step for those who know calculus, because calculus is not prerequisite. So I just highlight what might be needed, but you don't need to worry about that. So can you see my slides? Can you see my slide? Good. So we're briefly, so saying this is trying to prove why the normal mu sigma when z is equal to x minus mu over sigma is equal to normal CO1. Okay. The answer is when you rewrite z is this is z, right? Z can be rewritten as x plus z, right? You can, sorry for, right? You can replace z as x minus mu over sigma less than z. You can put everything there, you become this one. Okay, you just put x the subject. And then this one, right, is the cumulative distribution, okay? And from here to here, we require the technique called substitution. Basically just said x minus mu over sigma is t, okay, substitution, t squared. And this one cancel out this guy, and this one will become, you put this to here, you become c. Okay, so that's the method. Okay, as I said, I mean, for those who don't know calculus, you can basically forget about what I have just said, but there's some idea how we prove it. Okay, and the next one again requires some small calculus. I just highlight the key step here. Again, it's a substitution method. Okay. And just simple integration. And this integrate because square, right? Positive infinity, infinity, it gives you 0. Okay. So that's why 0. And here is don't have calculus, but just a standard linear property, right? Mu and sigma are number, right? So that's why you can write mu out and sigma out, and this is 0, right? So that's why only mu. Okay. Any question? And for this part, I just highlight second moment is z square, and this just then standard substitution method. Okay, and here is integration by part. Okay, and again, this one will be 0, and this guy turns to be this guy. Okay, this is integrating probability. This is 1. Okay, because the sum of probability must be 1. Okay, so that's the idea how you get it. But anyway, as I said, it's not math class, so just give you some very rough idea how you get it. Okay, and the proof of the variance is just use the formula. This is 0, and this is 1, so that's why 1. And this is using the linear property. Okay, mu plus sigma z. Mu is a constant, so you ignore it, and sigma I can take out, so sigma squared. Okay. I don't think I need further this discussion on this. So I just give you some idea of the following. So we state without proof. Okay. So what it means is some property, we don't prove it. And this property, you can just need to know it. There's no understanding or not because we are not proving it. Okay. So what it said, sum of the independent normal is also normal. So what it means is the normal, okay, and the independent, some of them still have normal, some of the mean, and variance, some of the variance, okay, because independent, okay, which means the covariance x and y is 0, okay. But the good thing is normal. If a bell plus a bell is also a bell, so that's what it means. One bell plus two bell is also a bell, okay. And same for difference. One bell minus the other bell is also a bell, okay. So that is something you need to remember in your mind. Is that okay? I mean, there's nothing to understand, but just to remember, there's a property there. Any question? Is that any clear? No, if no, that is the key thing is two normal add up together will not be two peak. It's still normal. Yes, very good question. That's very funny. It's still single peak. Yes, it's very funny, right? You can try. Turn out to be two. Yes, you can use Excel because you're looking at the Z table. Yes. Same for the quiz or assignment or your I think your final test. Also, you can use you should be using the Excel. Okay. Any further questions? It's very weird, right? Because someone have asked why I have one bell, okay, plus another bell, okay. Why I shouldn't expect something weird. Turn out to be it's very interesting. Two bell add together still one bell. Okay, turn out to be it's still something like this. Okay, actually it's not here, but it should be to be appropriate should be somewhat like here. I hope that would answer the Peter's question, but this is what supposed to look like. Okay. Any further question? If no, any question? If no, then the rest of the slides will be just a preview of the something we need in the future. So the quiz is up to here. But otherwise, we will just talk a little bit, some result that we will need in the future, but just very brief. Okay, to give you some idea, we will consider chi-square, T and F. Okay, just give you a very brief idea what they are. Okay, and so here we have with a normal, standard normal, right? With mean 0, sigma 1, okay? And suppose we draw a number here, okay? Then that number I square, okay? I draw a number here, we call x. I squared, right? Suppose x squared, okay? And how does it look like? Because square, it should be something like this, right? Start from 0. There will not be negative, right? So how this square looks like, we will call chi-square. Okay. Why chi-squared? Because actually it's x squared. But the one in the old day, the printing guys, when they print the thing, they pick up the small stamp, right? Then chi and the x are very close, like chi, right? They can't distinguish chi. I think it's a Greek letter. The Greek letter, right? And then they can't distinguish the two. So the error continue, the mistake in history continue, then that's why we call chi-square. Okay. But what is chi-square? Just you take a normal distribution, okay, pick up any number and square it. Is that okay? Okay. Equal degree of freedom is 1, or degree 1. Okay. It's 1. So you can see degree 1, you should expect what's degree n. Degree n is the sum of n standard normal, okay, the independent. So one of them, two of them, n of them chi-square n. Okay, basically just draw 1, square it, draw a second one and square it, draw n of them is square n. Okay, so this chi-square n. Is that okay for this one? It's nothing to understand, but just something you need to know, or later you say you remember. There's nothing to say understand up, but just definition, because they're defined in this way. Square of the normal is called chi-square. Many square them together, add together is called chi-square n. Okay. The quiz will not, well, the quiz will not be, yeah. The quiz will, you can forget about the quiz for the chi-square T and F, but you'll be using it soon. For the rest of the class, you'll be using the chi-square T and F. So whether exam include, well, of course, at the end we include, because then you'll be there in the next few classes. Basically, actually, in fact, you'll be using it very soon. Okay? I hope I answered the question. Alignment. So the chi-square looks like this, as we said. Either look like this or look like that, but something very weird. But turn out to be, if you have chi-square many, then maybe looks much like a binomial, right, or a normal. But anyway, it doesn't really matter to us. Just the shape look like this. And the next piece is, I think it's very important, T distribution. Okay. Sometimes in the textbook refer to student T. Okay, in some textbook, students T, because student is a guy under the pen name called, to write this, who invent this, under the pen name called student. Okay. Okay. Hilarious, but anyway. So what is student t? Okay. Turn out to be a fraction. It's a standardized normal at the top. Okay. And the denominator will be the chi-square of degree of freedom m divided by m. Okay. And take a square root. Okay. Something very weird. Okay. Then if the m of them we call degree of freedom m. Okay. What is degree of freedom? We don't explain it now. Probably become more clear in the next class, but you can just say m is some parameter, right? Like in the exponential with lambda, normal with mu, and sigma square, uniform with a and b, just some number there. And for chi-square, also n, for t is m, and what it is will be more clear later, and we don't explain now. We'll be next class. Okay, just to let you know that's how this t is. It'll be clear what it is. Okay, and this is turned out to be, I think this is the most commonly used one besides normal. Okay, this is the thing mostly you use for this class. And one important property is when m become infinity very big, this t of m will be a standard normal, which is normal 0, 1. Okay, so that is the main thing. Okay, probably you want to know, but you'll be evident when you see the slide of next page. Okay, so for the red one, okay, the red one, degree of freedom 1, and the blue one is degree of freedom 5, and the green one is degree of freedom 20, and the brown one is degree of freedom infinity. Actually, this is the same as normal 0, 1. Okay, and why this is true, we don't explain now, but later you will see. Okay, this is very useful when we talk about hypothesis testing. Okay, we're using this all the time, and we have estimation. Okay, we'll be using all this t all the time. Okay, so don't worry, you don't understand, you'll be using it all the time. And so just you can say a general preview of the what we are using. Okay, but don't worry, we'll be using this. And last one we're using for this class we call the F distribution. Okay, this we'll use it as a class in ANOVA. Okay, and regression we will talk about this too. And it's a ratio of chi-square. As you can see, x has chi-square m, and y has chi-square n, and the independent, then x over is degree of m, and y degree of n will be a what we call F distribution with mn degree of freedoms. Okay, do note that f, m, and n is not equal to f, n, and m. Okay, there's a little bit different. When you look at the table or type in Excel, you have to distinguish mn and nm. Okay, they're not symmetric. They're not symmetric. Okay, and this graph will be similar to this guy. It usually depends on how it looks like. When degree is large, it looks like chi-square. If the above is lot, then it looks like the downward slope exponential. Okay, I guess that's pretty much of this set of slides. But as we said, we have a quiz 3 next class, just to make sure you have any question. So the quiz will be exclusively on the continuous distribution. without t, chi-square, and f. Just uniform, normal, and exponential. Because they're so important, we need to have a quiz on that. And as I said, the quiz is attendance based, so if you don't fully follow, it's fine. But I hope you take the revision. Any question? No? If no, then we are going to talk about the sampling distribution. Can you see the new set of slides? I hope you do. Any question? Okay, that's okay. You can see my slide. So let's talk about what we call the sampling distribution. Okay. So probably go back to a little bit why we want to do this and onward what we're doing for the rest of this class. Okay. So far what we are saying is, okay, what we said is we describe population, okay, or what we call the sample space. Okay. And what we learn is, okay, if the sample space satisfies certain property, right, then the random variable generated by this, right, might follow some uniform or binomial, right, or Poisson, right, or exponential, or normal, okay, all those kind of things. And what's the use of those, right? And we don't talk about data at all, right? Except the first class of the data. And suddenly, we don't talk about the data, right? Now we are going back to data from now on. Okay, for the rest of the class, we are focusing on data. Okay, what data is? Okay, data is something we want to study, right? For population, right? And we are trying to get some idea of the population, what we call sampling, right? Or sample. That's what we want to focus today. Okay, sampling. We want to get some thing from the population. Unless we have the time and resources to study every single element in the population, we are usually trying to study part of it, right? We're trying to pick up something, okay? And that become our data, okay? And from these, we try to infer what's going on here, okay? That's the idea, okay? And if we know the population is following certain kind of distribution, okay? If from data, we can, based on what we have, we can estimate what kind of the value is, right? Suppose, remember, we have the exponential, right? Or Poisson, we have, say, Poisson, we have a lambda, right? Or binomial is NP, right? And if we have way to estimate this, right, based on data, right, then we can do a lot of things, right? So how to you estimate this? The first step is to collect some data and try to infer from those, okay? And for example, you want to see how many people are supporting Trump or not Trump, right? It's some kind of binomial, right? And you want to study it, you need to do some sampling, okay? And based on the sample, you infer data. From data, you want to see whether those claims are true or not, okay? you make some claim about the population, right? And you want to see the claim true or not. That will be the idea we will learn later. We call the hypothesis testing, right? We want to see whether those claims is true or not, right? Suppose you want to see a drug, whether it's going to be have a effect, right? Or not, compare drug A and drug B, right? That's hypothesis testing. And sometimes we want to do estimation. Also, we get from data, right? You be the topic of the after the sampling, we do estimation, right? When to estimate, say, how many. Suppose we do the right? We just the government just test how many people have the COVID-19, right? We're doing sampling, although we said, say, checking everyone, right? It's not going to do the survey, right? We're going to do sampling, right? And then we try to see, oh, out of almost 2 million, you have only 30 something cases, right? Or somewhat like that, right? Then you try to use this to guess how many in the Hong Kong, how many of them would have the virus, okay? It's rule of estimation. Okay, hypothesis testing with policy, right? Checking the medicine, right? And the next topic is ANOVA, right? It's trying to check whether grouping can help. Maybe you want to see whether the old people or young people, is it the rate of infection is same or not, right? It's a grouping method, right? And the last topic is regression, right? Say you want to see if enough sleep is going to help you to defeat the disease, right? We run a regression, okay? But all these methods we learn the rest of the class depend on data, right? Because we are making a judgment or what we call statistical decision based on data, okay? And the data you collect must be accurate, right? And that is the goal of today, to study the data, okay? It's called sampling. Is it okay? It's okay why we want to do all this thing. That's the goal of the rest of the course. Anyway, regardless of what, let's get started with the random sample. Okay, we call simple random sample. The reason we want to talk about this is because this is a basis of what we be learning. So, as we said, we cannot study the whole population, so we can rely on sample. And the sample must be representative. Okay. If the sample is representative, there is no point, right? Suppose I ask people who are go to the elderly home, okay? I ask, okay, do you want the government to spend more money to the elderly, okay? The answer is yes, always, right? Because no one would reject money, right? But if you ask the general public, people would weigh again against whether you spend more money on the elderly or spend money on the children or the young kid, right? There's a trade-off between the two, right? So if you ask the kid, right, whether you would want to increase the government spending on college education, high school education, kindergarten, right? They will say yes, right? So that's why if you want to get some opinion or set some idea on what's going on, it must be representative, okay? And representative, the basic thing is you make sure every element has equal probability being selected and is selected independently, okay? And by doing so, what you get a sample will be representative, okay? And selecting equally and independent is very hard idea, right? Because look at the map, say, of Hong Kong. Sorry for the drawing. I try to draw better, but okay. Just imagine this is Hong Kong, okay? Just for the sake of illustration, okay? How to have equal probability being selected is very hard. The reason why is Hong Kong is not a uniform distributed in term population, right? So I hope those who you don't live in Hong Kong, even with some idea of Hong Kong, right? Hong Kong will be along the harbor, there are a lot of people, right? And there's some people in the Repulse Bay and some people in Aberdeen, right? And there's few people live in the peak, and that's it, right? If you need to make equal probability, you need to make sure that you know how population density of each area and you do survey as such, okay? So you have to be very careful to get the equal probability, right? So usually that's why sometimes we call stratify the sampling is try to make sure you cut this population into different subsegment or district, right? And then you would do things as such, right? So if you go to the peak, you should sample fewer. You go to this area, you sample more. This area, you should not sample much, okay? And same idea if you, all the time you receive phone call, right? People ask you some opinion, right? And in those cases, usually every element, okay? Usually this assumption will be wrong because people like me, right? I usually don't pick up phone call, right? Because I worry about scam, right? So that's why I usually don't pick up phone call. So if you want to contact me, it's easier to contact me by email, right? And is it equally selected is also very difficult, right? Because I have my phone and maybe my parents or my family have phone, but if I don't pick up, probably they also don't pick up too. So these things have to be very careful when you do uh, sampling. Say for those who do accounting major, when you do audit, right? You go to a warehouse, right? Which warehouse to pick, which thing to pick, have to be careful, okay? But simple random sample, but regardless of what you do, you want to make sure every element will be selected equally likely, okay? And how is it being selected? Have to be a little bit further discuss how you do it, okay? But anyway, uh, let's focus on the math, okay? This is the real world how to select the problem, but let's understand it how to do it in mathematically, okay? So we say x1, x2, xn random variable are the n observation from population, mean, mu, and sigma, okay? So they're drawn from there, okay? We will call this simple, okay? Random sample, sometimes we ignore the simple. Random sample, okay? If every observation has the same mean, mu, and sigma, okay? That means that mathematically means expected value of xi is mu and variance of xi is sigma square. So there's no I here. Every observation have expectation of mu and variance sigma square. And the other thing is covariance xij will be 0. Okay? For I not equal to j, of course. Okay? x1, x2 have no correlation. Okay? Or covariance is 0. Is that clear? What do you mean by random or simple random sample? Or sometimes you will call IID, independently and identically distributed. Okay, you see some you call independent and identical, independent and identically distributed. Okay. Okay. Next, we start the definition of the first. Okay. Sample mean is the mean of a sample. Okay. Looks, I didn't explain anything, but this is what it means. Okay. Sample, right, has a random variable x1, x2 up to xn. Okay. Remember, they are not number, they are random variable, because from some distribution you draw a number. Okay. Uniform take of a number. Okay. Number can be anything, depending on what you draw. Okay. And these are all random variable. And what we ask is sample mean will be sum of all these random variable, right? The x1 up to xn and divided by n. Okay. So as each one is a random variable, right? So the mean is also a random variable. Is that clear for this one? Okay. And it really, the sample mean, it really depends on what you draw. Okay. Because suppose this is normal, right? Suppose you draw here, okay? Then the sample mean can be very large, can be different from the mean, the true mean itself. Okay. And suppose you draw something like very negative, it will be below the mean. Okay. It depends on what we draw. Okay. And usually, right, what you actually drawn will be here, 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 here. Mu, the x bar can be here, right? Or sometimes you draw another thing, you draw a sample of this. Okay. The x bar will be here. Okay. Before you draw, you never know. Once you have drawn, then it can be anything. Okay. Can be anything. Okay. So is that okay for the sample mean? Okay. So I want to say now is very interesting feature is the expectation of a sample mean is population mean. Okay. Remember, this assumption is true when you have a random sample. Okay. It's only true when you have random sample. If it's not true, that is not the case. Okay. It means what? You would be doing random sample. You draw things. Each time you have a sample mean, and the average or expected value of the sample mean is the population mean. Okay. In the other words, it means if you sample many times, okay, the average of all these sample mean. Okay. So to give you another idea, okay, this is the mean mu. Okay. What I said is, suppose you draw first sample, okay, just follow this number. It's called x bar 1. You draw another sample, okay, give you x bar 2. You draw the other one, okay, maybe x bar 3. You draw many of them, okay. At the end of the day, you add all this together. You do it many times. Suppose you do m times, okay. You do a lot enough, this will be exactly the mu. Okay. Let us do it graphically. Okay. Suppose this population. Okay. Have a lot of data point here. Okay. A lot of object here, right? Because population. And first time you may do this sample, come with x bar 1, and you do another sample, okay, with x bar 2, because sample random sample, right? You may end up with some overlapping. You may here with x bar 3, you may have more and more, okay? X bar 4, you do many of them. The average of this will be same as the whole population. The whole population have the population mean mu, okay? And what we are saying is the average of all these sample mean, okay? No matter the sample size is, will give you the population mean, okay? And we will talk about this in the next chapter. This nice property is called unbiasedness, okay? Which means that on average, we're hitting the target, okay? I guess that's pretty much of today. I guess your time's up. But we'll talk about example next class, but just give you some idea of this today. Okay, any question? If no, then stay safe. Thank you. Bye-bye. And then we will be, remember the quiz. We'll do quiz in the next class. Stay safe. Enjoy more hot pot, I guess. It's a good time to have hot pot when you have a typhoon number 8. In the old days, you play mahjong, but I don't recommend you to do it. So I stay to answer any question you might have. Thank you very much. See you around. Thank you.
Hello Professor， 我想問下咧，
大聲啲得唔得？
喂，係聽唔聽到
？OK 啦。
我想問下咧，當你整 skewness 嗰個 graph 嘅時候咧，其實 skewness 呢個 graph 係咪淨係可以俾一啲唔係 category 嘅數，即係佢只係可以連續1、2、3、4、5，跟住即係個 x-axis 要係1、2、3、4、5，佢唔可以係一啲 category 嘅嘢。
category 嘅咁就冇乜 skewness 可以講。
好啊，咁即係如果
數字先有 skewness 㗎嘛。
咁如果我嗰個 assignment， 如果我想講關於係國家嘅數據啦，咁樣唔同國家嘅數據，咁樣係咪就唔應該用 skewness 呢個圖？
可以有 skewness， 因為 frequency 嘛，你譬如話呢個國家係30，嗰個國家40，嗰個國家50，咁你咪可以變咗做嗰個數據啫嘛。可以有 skewness 㗎一樣，即係你個 frequency stable 啫嘛。我唔知你講邊樣嘢，但係譬如話你個問題係你個數據係譬如簡單嚟講，譬如話中咗肺炎啊，肺炎幾多人？咁譬如話 country A 有幾多人 ，country B 有幾多人 ，country C 有幾多人，咁呢樣畫到個數據嘅。
因為咧，我唔知點解我試過用 Excel 整嘅時候咧，佢嗰個 skewness 嘅圖係啱啱好相反咯，即係佢嗰個方向係完全相反咗。
咁我就答唔到你喎，咁樣我呢個。
好。
你咁我答唔到你，除非你發咗個電郵俾我睇下，我係點，因為我而家咁樣係你唔知點樣解釋俾你聽，因為我唔知你個問題係咩。
好。
你明唔明？如果你想再問一問你 detail，你發個電郵俾我，或者你再講清楚啲咯。如果唔係我都唔識點答。但係如果功課嗰度嚟講咧，就係 skewness 同埋佢通常如果佢覺得冇用，可以唔使加嘅。即係要加咩加？你覺得冇用，如果覺得係冇乜用就唔使加，唔一定要加。
因為個 instruction 嗰度話 shape 啊嘛，所以我以為一定即係 shape。唔一定要加，
因為你係我係講咗就係話你要表達你要表達嘅嘢，即係你想個 data 裏邊話俾人聽啲乜嘢咧，最重要嗰點得㗎。
好啊，唔該。
OK。Well, someone asked me the description of the sample drawn normal. Need not be normal, but we will tell you that the sample mean at the end. No, you don't need to normal. Can be anything. You can draw here, as I said, right? Can be drawn from some chi-square, binomial, anything. We don't know anything about the population. It need not be normal. Need not be normal. Can be anything.
Professor，我想問下咧，
請講。
嗰條1分鐘嘅片咧，即係 MP4 嘅形式，咁係即係要 show 住個幅 report 或者幅圖，然之
乜都得，你想點做都得，唔一定要 show 住個幅圖嘅，你可以畫幾個字得㗎。
哦，
你好似蘋果教主咁，係咪一個字得㗎？即係你睇下點講都冇問題。whatever you like。
OK。
就係想睇下你嗰個練習下你嗰個做報告嘅表現 presentation skill 咁解。
好，唔該。
得唔得？
Professor，
係你講。
我想問下如果我例如我想做佢嘅 demographic 啦，即係想話可能佢嘅 age 或者 gender 嘅比例咁樣，但係如果佢 source 純粹淨係佢已經直接 show 咗出嚟，話佢已經幾多 percent 啦，咁其實係咪已經冇乜嘢好嘢分，冇乜嘢可以再分析㗎啦？
咁你咪你講你係講緊個 homework 係嘛
？assignment 㗎。
assignment 嘅話，你就係你個數據你想表達俾人聽個數據有啲咩得意嘅嘢㗎嘛？
因為想 show，因為我呢個當係一個直播平台咁樣啦。
咁如果你覺得有得意嘅，如果淨係個 ratio 都得意，咁就都夠㗎啦。個 ratio 已經係 mean 嚟㗎啦嘛。
但係佢連個 sources 即係直接，佢冇一個好 exactly 嘅數字，佢淨係講可能例如佢個男同女嘅比例係65:3。
但係如果個問題係你我嘅意思係個功課係叫你從 data 開始啊嘛。如果你淨係得個 summary statistic 咁就唔係符合咗功課嘅要求，係嘛？
所以其實就冇乜嘢再分析嘅。
係啊，除非如果你係嗰個係每一個國家或者每個地方嗰個，咁你咪有 mean 有 variance 係嘛？個 data 有 data。如果你淨係得個數字嘅話，咁就唔係好符合個功課嘅要求。
好啊。
但係如果你個 data 係有數據係有每一年做有幾年嘅，有1-2年嘅，咁你都係算有 data。
因為佢淨係例如佢2019年，但係直接佢淨係因為我揾唔到 exact 嘅數字，佢直接已經俾我可能16至24歲就40%，即係55至64就3%。
咁都算有嘅，咁你可以講翻整個年齡段係幾多咯，都有啲嘢可以講。
唔係，即係佢有個 base，即係可能佢有1萬人去做嘅，但係佢淨係話一 base，但係佢冇 exactly 16至24歲係幾多人。
佢冇 data 俾你咩咯？係咯，佢冇 data 俾你，即係你冇 data 噶嘛。
佢就係得個 base，跟住就直接 show 40%咁。
原意個功課係想要你做個從 data 去得出個數字。
哦，即係其實做唔到嘅。
你淨係得個你而家就攞到 summary statistic 啊，咁就個唔係咁好咯。如果你攞到幾年嘅咁咪好啲咯，或者你可以 compare 唔同國家嘅數字就有趣啲咯。即係想你處理數據㗎嘛，佢係 data 㗎。如果你淨係直接攞咗佢最後嗰步，咁就唔係咁達到嗰個功課嘅要求啦。
好啊，係。
Any more questions? Just
我想問喺頭先
so I stay 2 to 3 more minutes.
喂，聽唔聽到？喂，聽唔聽到？
喂，
聽唔聽到？
我聽唔到，可唔可以大聲啲啊？因為我真係聽唔到。喂，
聽唔聽到？
好細，聽唔到，好細聲。你可唔可以大聲少少咧？再
聽唔聽到？
好微弱，我試下你講下睇睇得唔得咧？
喂，唔知佢喎，好細聲。OK，喺頭先個 chi-squre distribution，即係上一個 PowerPoint 咧，佢 即係畫個，即係佢會俾啲例子話chi-squre degree 係 1，degree 係 3，degree 係6咧。點解個 chi-squre 1個 distribution 唔一定係0到1之間嘅
chi-square 1唔係0嘅，係 normal 0 1，咁即係話佢嘅 square，所以佢係 normal 係0到 infinity 噶嘛，唔係 normal 係 negative infinity 到 positive infinity 噶嘛，咁所以佢係0到無限大嘅都係。
哦 ，OK，
即係佢可以 x 係可以好大噶嘛，好大嘅 square 都好大㗎嘛。
OK，
得唔得？因為我唔係好確定，我聽到你講嘅嘢，但係我唔知答唔答到你啦。
OK，
因為我真係聽唔係好清楚。不過我希望答到，我希望答到你。你個問題係咪問點解 chi-square 1嗰陣時唔係0到1之間係嘛？
係。
哦，佢因為 x 係 normal 係負無限大到正無限大㗎嘛，咁所以佢有 chi-square，咁佢都會係0到無限大咯。咁得唔得呢個
OK。
咁睇下大家仲有冇問題啦？如果冇問題，咁就到呢度先啦。OK，唔該晒。